Hello, welcome back. We're looking at Newton's laws of gravitation, and um, we're looking at mass equals velocity, or force equals mass times velocity. And in this equation, force equals mass times velocity, there is a whole lot of things that you can bring out of that. And so we just talked about how you can take force equals mass times acceleration, and you can actually derive out of that all the stuff you need to solve for the time of anything going around another thing in space, where the time or period of a satellite going around a central body. All right, so we also looked at how you could take force equals mass times acceleration and derive out the velocity of a satellite going around a central body. Now, what about gravitational field? So the idea of gravitational field is simply that if we have a central body here, right, what it's going to do is it's going to exert a force on all the objects around it. So if you have a satellite that is going around that central body, it is within that central body's gravitational field. Now, the idea with the gravitational field is the further you get away, the weaker the gravitational field is. Now, I talked about how last time the gravitational field is the acceleration of gravity. It's basically the acceleration that is needed to keep this, or that is pulled on this, that's pulling it toward the center of the center. So force of centripetal equals the gravitational constant, or this gravitational equation that Newton came up with. And so it also equals, force of centripetal also equals mass times the acceleration of centripetal. So mass of what? So this is the mass of the satellite, right? So if we separated this, we could say this. We could say that the force of centripetal here equals the gravitational constant times the mass of the central body divided by the radius squared times the mass of the satellite. And then that right there is my acceleration times mass. And so that means that acceleration equals the gravitational constant times the mass of the central body divided by the radius squared. And what is the acceleration? The acceleration is what is required to pull, is the force, right? It's what is required to pull that thing toward the center, which keeps it going around in a circle. So acceleration also, of course, equals, because force equals mass times acceleration, right? So acceleration also equals the force divided by the mass, right? So if you're trying to figure out the gravitational field, or sort of the effect of gravity on any sort of satellite, like near or away from a body, if you know the force acting on it and you know the mass, you can divide just the force by the mass to find it. And you can also, instead of just calling this acceleration, we could call this little g. So little g, or what is sometimes referred to as a gravitational field. So oops, this is sticking on me. A gravitational field, right? Little g. And we know that the gravitational field when you're on the surface of the Earth is 9.8. And I showed you another video where I showed you how this right here proves that right there. And actually, if you watch that video, you can see how the acceleration of gravity is this part of the equation right here, because we pulled that out in that other video. So gravitational field, little g, equals the gravitational constant times the mass of the central body divided by the radius squared there, or just the simple force divided by the mass, right? Or a whole lot of other things. So you can take this equation right here, this force equals mass times acceleration, and you can do a whole lot of awesome stuff with it. So in the last 3 videos, we showed you how you can solve for the period of a satellite, the velocity of a satellite, and now the gravitational field that's going to be affecting that satellite. So you can see actually the acceleration that it will have at whatever distance it is away from that central body.